Okay, so the previous two videos kind of lead us into the topic of electric field strength. So very similar to gravitational field strength. So before we had the G vector, all right, so that was gravitational field strength. Now we have the curvy back E, which is our electric field strength. So there is what we were talking about today. So bring that down to there. So electric field strength, and there is your symbol again with the vector symbol, at any point is defined as the electric force per unit positive charge, and it's a vector quantity, which means that it will have both magnitude and direction. All right, so it has magnitude and direction. So very important when you know that it's a vector. So electric field strength is electric force calculated from Coulomb's law divided by the charge. So curvy back E is electric field strength. Fe is your electric force, and our units are newtons per coulomb. All right, and my formatting's kind of gone wonky on me here. So this charge should be tabbed over a little bit. So I have to take a look to see what the printout that you have looks like, but those guys should be over. And the units, you can circle this. That's its own right there. Newtons per coulomb. So if you recall, I'm going to compare it back to gravity. So G, gravity, the units were newtons per kilogram. So electric field strength is newtons per coulomb. So there's tons of parallels between our gravitational forces. So because this is an analysis of field strength, we're looking around one of the charged points. We can incorporate our equation then from yesterday. So that one that I'm referring to is Coulomb's law. So there's our Fe. Then, again, my formatting is gone completely. So I will fix it up. So electric field or electric force from yesterday is KQ1 Q2 over R squared. It should say then electric field strength, which is Fe over Q, would then equal K Q1 Q2 over R squared divided by Q. So Q is our charge of the second particle. Okay, so that Q is really equal to Q2, which in the end means that the Q2 and that Q will cancel. So remember, it's similar to mass of the Earth. It was always GM over R squared. Well, it's the charge of the source, which is really very important. So it ends up being K charge of your source over R squared. All right, so there is our formula that you want to get onto your study sheet. And again, that's measured as newtons per coulomb, and it is a vector, so you will need to get directions when you give answers. All right, so there we go. Moving along then, let's take a look at its application. So what is the electric field strength? 0.6 meters away from a small sphere with a positive charge. So what are we given here? I know an R, I know a distance between two objects, and I know the charge, and that is the charge of my source. And K is a piece of given information. So I can calculate electric field strength around this sphere, K Q1 over R squared. So K is your 9 times 10 to the 9th. We just got the charge there, -8. That's all divided by the 0.6 squared. And we get an answer of 300 newtons per coulomb, and it's going to be toward the charge. All right, so what does that really mean? I'll give you a quick picture just to emphasize. So here's my little positive charged particle. I'll draw in my equipotential line. That equipotential line is at a distance of 0.6 meters according to this question. So that tells me that the magnitude of the field strength is, along this point at any given point, 300 newtons per coulomb of charge. And that could either be repulsion or attraction. In gravity's case, it's always drawn toward the center. But that's because gravity is always in a state of attraction. Here, when you're talking about a charged particle, if it's positive, it could be pushing it away at 300 newtons per coulomb, or it could be attracting it. So it's a either-or situation here. All right, so that's how you would interpret the answer provided. Next example. So now we have two charges. One of, so Q1, 3.2 times 10 to the negative 9 coulombs. And the other one, I'm going to call it Q2, is negative 6.4 times 10 to the negative 9th coulombs. And they are 42 centimeters apart. Make sure you convert that to meters, 0.42 meters. Calculate the net. So what we got going here, the diagram always helps us out. We have a positive charge, that's my Q1. We have a negative charge, which we would call Q2. We know that they are 0.42 meters apart. And we want to calculate the net force at a point P. So point P, which is 15 centimeters, or 0.15 meters from charge 1 on the connecting line. So that means that they are, point P is directly between. There we go. So you can do this two different ways. We could say that, and it doesn't really matter whether you want to do this in stages, but we could say that the total ET, electric field strength, is equal to the electric field strength from charge 2. So again, I'm going with the convention of this being my positive directions. So I'm going to assume that it's going, the attraction is going to be greater, or I'm assuming the right to be positive, I guess, minus the field strength from point 2. Okay, and you can break this in stages and do the subtraction at the end if you so choose. So E2, doing that calculation, so it'd be K Q2 over R squared minus K Q1 over, now we're going to have two different distances here, so I got to be careful, making sure I have an R1 and an R2. Plugging in my numbers, 9 times 10 to the 9th. Q2 is the negative 6.4 times 10 to the negative 9th, divided by 0.1, no, it won't be the 0.15 squared, it'd be 0.27 squared, the difference between 42 and 15, minus 9 times 10 to the 9th, 3.2 times 10 to the negative 9 over the 0.15 squared. And what do we end up with here? I end up with this one being negative 790 minus, the other one's 1280. So that gives me a total of 2,070 newtons per coulomb. Oops, and it should be negative. So my convention, I assume my answer is to the right, which means that 2,070 newtons per coulomb to the left. Okay, so therefore, total electric field is 2,070 Newton per coulomb to the left. All right, so what that does is tells us that at that point right here, the equipotential line that's running through there, whatever shape it is actually pushing everything to the left at that point in time. All right, and that's because the charges are opposite. So if it was a negative charge in there or a positive charge in there, it would determine whether it's moving left or right. So you can substitute that in at a later point in time. All right, so on to the next. We have the magnitude of an electric field between two plates, which are parallel, with a capacitor is 3.2 times 10 squared newtons per coulomb. So the parallel plate capacitor is a fancy way of saying the electric field strength And you'll note that I can tell from the units that were given that it is electric field strength. So what's happening? I have a positively charged plate, a negatively charged plate, and we want to know what the magnitude of electric field strength, how would it change if the charge on the plates were doubled? What happens if the charge is doubled? Well, a couple things come from this. We know that the distance doesn't matter here. So we know for answer to A here, this is our formula for getting our formula, but the R doesn't change. So if we take E1 and compare it to E2 in terms of electric field strength, we would have K Q1 over R1 squared divided by K Q2 over R1 squared. The distance between the plates doesn't change. So what happens is our K's will cancel and the R's end up canceling because they're equal values, they're of equal terms. So we find that E1 over E2 is equal to Q1 over Q2. So a direct relationship. So something that you want added to your cheat sheet. So when we go and solve the question for A then, we find that the answer to A, distance, plays no role. Okay? Oh, sorry, it's charge for A. My mistake. So if the charge were doubled, if Q2 is equal to 2 times Q1, then E1, E2 equals Q1 over 2Q1. So very similar. So we'd end up with electric field strength equals 1 over 2. Simplifying, we find that E2 is going to be twice E1. All right, so just if we double the charge, we double the strength. Okay, that's what that relationship tells us. Therefore, strength is doubled. Now, the second one, what happens if we change the distance between the plates? Well, we notice that there is no R in our relationship. So for B part, E1 over E2 equals, not R, Q1 over Q2. And there's no R value. R value or distance. So therefore, distance between plates has no effect. No affect, effect, I don't know. Ask an English teacher on that one. Effect on E2. All right. So there we go with field strength. Just as a quick comparison, keep in mind, we talked about gravity. And we have electric. So we have our gravitational force as being GM over R squared. Well, electric force, Fe, is KQ Q2 over R squared. And when we look at the field strengths, gravitational field strength is Gm over R squared. And our electric field strength is KQ over R squared. So you can see there are similarities, which is very, very interesting when you think about it, because they're two distinctly different fields of study. One is classical mechanics, the other one is a field of electricity. You wouldn't think that the relationship would exist between planets and charged particles, but it's almost, it's actually quite, makes you feel good about science that there is that sort of closure or circular nature of it, that a lot of things are tied together. So that now allows you to do the homework that talks about field strength. So it's there on those pages, and having any trouble, make sure you let me know, and I can go and explain any part component of the lesson if you had trouble with it. Good luck, and we'll see you tomorrow.